actually going to start with a question that was asked about today, and it had to do with the closure of exponents. So we're going to look at algorithms for whole number multiplication and division. But the first thing we need to talk about is exponents. So definition of exponents first. If you have a number to a power, and that power is itself a whole number, then anytime you're talking about actually a natural number, which got used here, then it's just a repeated multiplication. So all exponents are is repeated multiplication. Kind of like all multiplication is actually repeated addition. Okay, it has that same kind of feel to it. The first thing I want to show you is the properties of exponents, and then we're going to actually work some of that out into the why it works business. So you guys gave me an example of this one earlier on the board. When we have two powers, a to the m, the same base, and a to the n, and they're multiplied, what happens to those exponents? Okay, that wasn't what I wanted to do. I'm sorry, just a sec. All right, so we have to add the exponents, right? A to the m plus a to the n. And the rule number 2 is very similar, property number 2. So instead of them being multiplied, now they're divided. So what happens to the exponents? We subtract, yeah. All right, number 3 looks kind of like number 1. So somebody tell me what's different between 3 and 1.
You're raising it.
Okay, so I'm hearing a couple of things, so let me hit on what I'm hearing. So Mackenzie said something about the fact that they're not separated, right? They look like they're sort of enmeshed together. And then Lauren said something about the fact that it looks like it's raised to another power. And those are the things that you should notice. I don't want you to confuse properties 1 and 2 because they actually have a different result. One of them, property 1, has 2 separate bases. They're the same, they match, but they are 2 separate bases. The second one is in fact a power raised to another power. So when we have a power raised to another power, what happens if I want to write this all combined? Multiply it. And then the last one, number 4, we actually see 2 items inside the parentheses raised to a power. What's that going to result in? All right, so each of the exponents, or each of the factors inside can be raised to that individual exponent. It kind of feels like it's a distribution thing going on, right? Okay, it's not distribution, it's actually just a repeated multiplication feature, but we can actually put the exponent on each individual factor. And then there's this definition down here that you have probably seen before, and I'm going to talk a little bit more about why it works later too. I'm not sure if that's this class or if it's later, but if you have a power of 0, then anything to a power of 0 is value 1. Okay? All right, so what I'd like for you to see today, what I'm going to do the examples of here first, is we're actually going to work the problem out like we didn't know the rules so that you can see if the rule really does work. Okay? I don't want in your homework for you to do what I'm about to show you. That is not my intent. Okay? My intent is to show you that these rules did not just sort of appear out of nowhere and somebody said, lo and behold, there will be a rule and it will look like this. No, it's not what happened. Okay? I want you to see that it really does work. So if you really did it out longhand, it would be okay, but that's not the point. The point is that you've got these simplified ways of doing it. We're going to use a simplified way of doing it, but I want you to sort of not just think it happened because some mathematician somewhere decided it really does work, and that's why it's used. Okay? All right, so the first one, the first property, we already wrote this down, is that we add the exponents together. So what does a cubed mean? What does it really mean? A times A times A. So I'm going to break this down so that we can see that this really works. We know what the answer should be. What should the answer be? A to the 7th is what the answer should be. Okay? That's the property says we're looking that we're going to see if this really works. All right, so this is A cubed. And then what does A to the 4th mean? All right, and so how many A's do I have? 7, I do. So a shortcut way of writing that would be A to the 7th. That's all the property is doing, is it's allowing me to not do everything that I just did to write them all out and then to combine them back together. But that's why it works. All right, so what should this one be? What's this property? Number 2. M minus n. And if I'm looking at these exponents, the answer should be what? a to the 1, and normally we would just write that as a. So let's see that work. So a to the 4th, you guys told me before, was a times a times a times a. And a to the 3rd was a times a times a. And then what do you know about reducing with fractions? Yeah, if they've got a factor in common, it will reduce, right? And I am going to use the word reduce because we use the word cancel too much to be too many different things. This is a reducing issue. And so what happens? What am I left with? A, which is also known as a to the 1. All right, third property, we did it a minute ago. It actually looks like I could write this as multiplication, right? So if I'm using that property, the answer to this question and what you would do on your problems on your book and whatnot would be that this answer is a to the what? 6. Okay, so a to the 6 is the answer. That's great, but let's actually see why that works and why it's really different than number 1 as well. So a to the 3rd means a times a times a, and this is supposed to be squared. What does it mean when you square something? Multiply it by itself. So this really means I have a times a times a times a times a times a. How many a's are there? There's 6 of them. So it's a to the 6th. Right? This is stuff that works. It works, so we want to see that it does. And then this one right here, number 4, actually should say a to what? A to the m, and then good. All right, so AB to the 4th should actually end up being A to the 4th, B to the 4th. And that's what you're going to do when you do on your homework. All fine. Let's actually see how that works. So what happens when we raise them into the 4th power? What does that mean? Right. We can multiply it by itself 4 times. And then you have had a whole, I'm not going to go through every detail of this because that's actually the ones you were looking at where it moves things around. That's the problem I'm at this point. I want to be able to move things around, right? I want to be able to move all the A's to the front and all the B's to the back. And I can do that with a lot of associative property and commutative property, right? I can move everything I want with those 2 properties as many times as I need to because it's all multiplication. So I actually can rewrite this with all the A's in the front and the B's in the back with those 2 properties used multiple times. And then my result, of course, will still be a to the 4th, b to the 4th. So I actually don't have the distributive property at all there, do I? I have the associative and the commutative property many times to make it work. Any questions on that? Okay, so let's actually do the kinds of problems you're going to see in your book. One thing that you need to notice when you're doing these problems, though, is that you're not going to see A's and B's. You're going to see numbers. Okay, which actually is, to be honest, more challenging than the A's and the B's. Because in order for this to actually work, they all have to be the same number. And if you notice on part A, yay, all base 5. On part B, no, they're not all the same base. So we're going to have to fix that before we can do anything else. All right, so taking a look at part A, which of those 4 properties do you think we're going to be using? Number 1, and what am I going to do? Add the exponents. And so if I add all my exponents, what do I get? 5 to the 16, and that is exactly what your answer is supposed to be. Please do not grab your calculator and type in 5 to the 16. That is not the point. The point is to simplify it and write it as an exponent, okay? You're all good with that? All right. Next one, I got a problem. Like I mentioned a minute ago, the problem is that I've got different bases everywhere. There are 2 ways to fix this. So, suggestions. What do you want to do with 6? Could turn them all into 6s. How could we do that? It will work, but you don't know how yet. Can't turn them into 12s. It's not going to help us. What if we do this? I'd like to use property number 4. You guys remember property 4 said? Because I don't know about you, it doesn't look like it applies here, but it really will. I would like to take these 2 right here and use property number 4 backwards. So what I mean is I want to start on the right-hand side of what your property 4 says and pull it back into what the left-hand side of property 4 says. So I can leave the 6 to the 4 here, and I can leave the 2 and the 3 inside. Those are the different bases with the 3 on the outside because they have the same exponent, don't they? That would work. This isn't the only way to do this, but this one would work. And then I have 6, like Brendan said. So this is 6 to the 4th and 6 to the 3rd, which would give me 6 to the 7th. This is one way to do it. Would you like to see another option? Okay, which is equally valid, and I don't know which one your book's going to pick on something like this. I really don't care. You can pick either one. The other option is instead of mushing the 2 and the 3 back in together to get 6s, I'm going to take the 6 at the beginning and I'm going to break it apart to get 2s and 3s. You following? Okay. So I could take this 6 and write it as 2 times 3 to the 4th. And then I've got 2 to the 3rd and 3 to the 3rd. Then I can use that same property number 4, but actually sort of in the forward direction of how we defined it. And I can sort of in this idea of distributing exponents, I can use that here. So this is 2 to the 4th, 3 to the 4th, 2 to the 3rd, and 3 to the 3rd. The ones that are the same get paired up. So I've got 2 to the 7th. And then I've got 3 to the 7th. You could actually leave it like that. That is simplified. That's okay. Or you could recognize that, hey, they both have a power of 7. I could multiply the 2 and the 3, write it as 6 to the 7th. But it would be okay to leave it as 2 to the 7th and 3 to the 7th. That's actually prime factors, which in some cases is preferable. So you could leave it that way. So either of these answers would be fine. You're using the same properties, but in slightly different ways for each of them, right? All right. We're going to move into something else. We're going to talk about the multiplication algorithms. Now, we did addition and subtraction algorithms in 3.2. Do you remember those? Had some add up things and some equal additions things, and we had some lattice multiplication at one point. We had a lot of different lattice addition at one point. We did a lot of different things in that section. This is the component of this section that's like that. All right, so the first one is the expanded form for the multiplication. So this actually is 48 times 32. I'm going to write it sort of the way that most young students like to see it written. They like it this way, don't they? Probably some of you do too. So what I want us to think about is I want us to think about expanding these. Now we did expanded form when we did addition, and instead of writing the 48 as 48, we wrote it as 40 plus 8. Do you remember doing that? And we wrote the 32 as 30 plus 2. Okay, make sure I don't jump the gun here. All right, so we're going to think about this as 40 plus 8 and 30 plus 2. And we're going to actually do something that you guys saw already happen on the board today. We're going to do this. We're not going to do it with a formula, but we're going to do this kind of a binomial expansion. So we're going to think of this as 40 plus 8 times 30 plus 2. And we're going to FOIL, okay? Multiply the first terms together. I'm going to show it to you in this form because I think this is the one your book uses. And then I'm going to show you another form here in a minute too. It's going to look a little bit more like our standard algorithm. And then I'm going to show you yet one more form that's extremely visual and it's very appealing to me. Maybe you like it too, I don't know. All right, so what's 40 times 30? 1,200. And then we'll go to the outside terms. We've got 40 times 2, which is 8. And we'll do our 80, right? Sorry. Our inside terms, 8 times 30. We get 240. And then we'll do our last terms, 8 times 2, and get 16. And then we can use whatever means we would like to add these together. We've got 1,200. We've got 80, we've got 240, and we've got 16. You've learned all sorts of ways to add these up. If you want to go back to what you feel most comfortable with, you probably add the 6 first. You'd have 8, 4, and 1, which gives you, what is it? 13. So I'll write my 3 down and carry my 1. Sorry, I carried it to the wrong spot. Do that again, carry my 1. Then I have 1, 2, and 2, which gives me 5, and then I'll carry my 1 down, so I've got 1536. All right, So let me show you another option for this expanded perspective. You could go from what's up here, and you could think about this. I'm just rewriting because I ran out of space. Much like what you do when you do our standard algorithm. You could actually multiply the 2 times the 8, and you can write down, oh, that's 16, right? So you've multiplied the rightmost numbers together. Then you can multiply the 2 times the 40. You can get 80. You can multiply the 30 times the 8, which then very clearly shows you why you have that mysterious 0 in the standard algorithm when you write it down. You guys know what I'm talking about? Right, when you do 48 times 32, and you do this, right, and you write down 16, and you have 896, then you have to put the 0 in here. Do you guys know that? Why do you do that? Yeah, you're multiplying the tens place, so you really aren't multiplying by 3, you're multiplying by 30. So you can see that happening here really nicely when it's actually written out. So this is 30 times 8. And, well, let me move this now. So you've got your 240, and then you have your 30 times 40. And you've got, what, 1,200? Okay, and it adds up, of course, to the same 1,536. I want to show you one other way of doing it that I think is, again, we're doing the same answer no matter how we do it, but it's really friendly because it has a great picture for it. Can I switch the slide? Okay. All right, this is called partial products, but again, it's just like what we just did. We're going to separate the 40 into 40 plus 8, and the 32 into 30 plus 2. But what we're going to do is we're going to write a box down. Make yourself a square and split it into 4 pieces. The only reason it has 4 pieces, this would actually work with 3-digit numbers as well, but we're using 2-digit numbers, so we're going to get a square that's a 2 by 2 square. If we had a 3-digit number times a 3-digit number, we'd get a 3 by 3 or a 9-unit square. I've got my 40 up here and my 8 here, and I'm going to put my 30 here and my 2 here. And what this does is it gives you a visual for the multiplication. In fact, it's even better than that, and I'll draw you another picture in a moment that actually shows that it can be done to scale. But what these boxes represent is they actually represent the multiplication of each row and column you're on. So from the first box right here, you're on the column for 40 and the row for 30, so 40 times 30 is 1,200. And then you do the same thing for the next ones, right? 8 times 30 is 240. 40 times 2 is 80, and then 8 times 2 is 16. And then we're going to add the boxes together. 1,200 plus 240 plus 80 plus 16. I don't know that I needed all those pluses. Remove a couple of them. It was 15 something. What was it? 36. Still get the same answer. So some of you might be thinking, okay, that seems like it took longer, and I agree. This is not an efficient way of doing it, any of these options. But let me tell you what it doesn't do that the standard algorithm, as you know, did. There's 2 things, in fact, that it doesn't do. One thing is it doesn't have that mysterious 0 appearing that you should explain where it comes from. But I suspect that some of you looked at that and said, well, you just put it there because you told us to put it there. Or it's a placeholder, but a placeholder for why? I mean, you don't understand exactly why. So if you're going to be teaching with the standard algorithm, there should be some sort of explanation of where this is coming from, why we're using it. The other thing that happens with the standard algorithm that's not quite so friendly, and you probably haven't sort of thought about it in years, is the fact that when you do this, you do 2 times 8 is 16. You write a 6 down and you carry a 1, correct? Okay. And then you do 2 times 4 is 8. And then what do? Add the 1. So what did you do? You did multiplication and addition all at the same time. Didn't you? Yeah. Okay, I mean, you guys know how to do it and you're comfortable with it and that's fine. But think about back to when you were first learning it. Maybe you don't remember, but I will tell you for sure. Some students go, I'm adding and I'm multiplying in the same step. That feels a little bit odd. And if you forget which one you're doing at which point, could you very quickly and very easily get the wrong answer? You bet. So the nice thing about these other 3 options that I've sort of written down is that they isolate which operation you're doing at any given point in time. You did all your multiplication first, and then you did all the addition. That's something kind of nice. There's a nice feature to doing it in that way, especially when you're first learning how to do it, right? You have to remember there's two things that you really would like to have. You'd like to have something that's very intuitive, I understand it, it makes sense to me, and that's kind of what's going on, particularly with this picture right here. And then you'd also like something eventually that's efficient, it's quick to do. So what you're used to doing is very efficient, but not very explaining, right? It doesn't really help you intuitively see why something works. I wanted to show you that this really works from your area perspectives as well, and you guys know one of your multiplication models is area, right? So think about what happens when you do these diagrams. We'll use this one. If you actually had 40 times 8 and you wanted to split this up, well, you'd split it up something like this, right? So this is 40 wide, and this is 8 wide. I ballparked it. I don't even know if it's straight, but pretend like it is for the moment. And then you can do the same thing for 32. Now, your picture wouldn't do this if you were just trying to get the solution, but you can see very quickly why, from the perspective of area, that this makes sense, right? You've got the huge number. This is 1,200 right here. You've got this little sliver right here that's going to be that 240. You've got a smaller sliver down here, although my picture's not to scale, of course, that's an 80. And you've got this tiny little box here at the bottom that's 16. So you can think in terms of area, how that's actually working with this particular picture too. Okay, you guys ready for another one? All right, so who's taking contemporary math? Okay, you have. You may recognize this one. This one's called the lattice algorithm. You've seen a lattice algorithm for addition in this class. I'm going to show you one now for multiplication. It is similar. We're actually going to take a look at 48 times 32, same one, because I want you to know that it works in all these cases. And I'm going to draw a square that I'm going to split into two boxes, and I'm going to talk a little bit more about the split here in a minute. Now, this one's different than the last one, so don't go put it in the 40 and the 8 and the 30 and 2. That's not what we're going to do. We're going to use the single digits that they actually have. So instead of writing 48, I'm going to write 4 and then 8. And then 32 is going to be a 3 and a 2. And it really matters that the right-hand side is where you put the 3 and the 2, as opposed to putting it on the left-hand side. If you don't put it on the left-hand side, you're going to run into yourself later, okay? So make sure that whatever you do, you put it on the top and on the right-hand side. And it really doesn't matter if the 48 is on the top or on the right, or the 32 on the top or on the right. You can switch them out. Okay. So this is what we've got so far. All right, so the next thing you're going to do is you're going to split each of your boxes in half along the diagonal. And that's why it's called lattice, just like we did with the lattice addition. It's because it looks like a lattice. Now, this is something of what some lattices would look like. Okay. And we're going to, instead of adding, because this is what we did before, is that we had a number here, we added, and we split it between two boxes. We're going to multiply, just like we did with partial products. So I'm going to take, instead of 40 and 30, I've got 4 times 3, and what's 4 times 3? 12. I'm going to write the 1 on top and the 2 on bottom. So each of these corners, each of these quarters of my box is going to be the multiplication of the row and the column it's on. All right, then I've got 8 times 3, which is 24, 2 on top, 4 on bottom. 4 times 2 is 8. So I'm going to put the 8, and it just goes on the bottom. If you want a 0 on the top corner, you can do that if it helps you, but you don't have to. And then I've got 8 times 2, which is 16. So again, this is really nice because it separated all the multiplication from any addition. And we're going to do some addition next, but it came all the way after the multiplication was already done. Are you with me? We're done with multiplying. So what we're going to do next is we're going to actually add diagonals together. So my diagonals, I'm going to recolor in another color so we can talk about them again. We're going to start in the bottom corner, okay, just like we did with the addition lattice for addition. And the bottom corner always just has a single number that we're just going to rewrite. There's no adding really to do. But the next row we do. So the next diagonal has a 4 plus a 1 plus an 8, which is 13. I'm going to write down the 3, and I'm going to carry my 1. Now I've got 1 plus 2 plus 2, which is 5. And then I've got a 1. And my solution then is the numbers along the outside. My answer is 1536. And of course you can check that with any other method that you'd like to make sure you didn't make an error in doing it. But now you can see hopefully why you don't want the numbers 32 to be on the left, because they would run into the sums that you just got. So we don't want them there. We need them white. Okay, you guys ready for the next one? Division. All right, division algorithms. There's actually only two, and one of them is the algorithm that you know. So I'm going to start with the one that you don't know, and that's called repeated subtraction. Repeated subtraction is very intuitive. It makes sense, okay? But it can become very cumbersome and very long depending on what numbers you're working with. Okay, so I promise you we're not going to work with ones that are going to be crazy long on any tests or anything like that. But I do want you to understand how it works. All right, so 620 divided by 5. All right, so what we do when we're working with repeated subtraction is we work by subtracting repeated values that are powers of 10 times whatever dividing by. So let me stop by that and say what I mean. We're dividing by 5, right? All right, so we're going to work by subtracting numbers like 5, 50, 500, 5,000, 500,000, 5 million, anything that has a 5 followed by a bunch of zeros. And the reason we're doing that is because we're dividing by 5. Okay? So all we're going to be able to subtract from this guy is the number 5 followed by zeros. Are you with me? So what is the biggest number that I can subtract from 620? 500. And I'm going to subtract 500, which is 5 100ths. So what you legitimately could be asked to do is only subtract tens, 100s, and then I'd actually have to subtract 100 5 times. I'm not going to do that. We're going to subtract 5 times 100. Okay. So what is 620 minus 500? 120. I can't subtract 500 anymore, correct? I'm not going to say positive. I'm only working in whole numbers, so I got to say positive. Which means the next biggest thing I can subtract is what? 50. Now I could have to subtract 50 more than once. In fact, I will, won't I? So we're going to subtract 50 here, which is 5 times 10. And when I subtract 50, what do I get? 70. And then I can actually subtract 50 again, correct? Sure. So if 70 minus 50 would be, which is 5 times 10, would be 20. And I can no longer subtract at 50. So what do I subtract next? 5. And I'm going to have to do it several times. 5 is 5 times 1. So what's 20 minus 5? 15. And I subtract 5 again, right? All right, so what's 15 minus 5? 10. And I'll subtract 5 again. 10 minus 5 is 5, and I subtract 5 again. And I get a 0. If you got a number down here that was like a 2, you just have a remainder of 2, just like with the other stuff, okay? But the answer then is, what should the answer be? Like, what did I do? Well, take a look. You have 100, 10, and 10. 1, 1, 1, and 1. And add them up. What is it? 124. Could you verify that with a calculator or by doing the standard algorithm? Sure, you could. So, what in the world does this do for you besides take a long time? Because it potentially could take a long time, right? Especially if I had to subtract something 9 times, which you potentially could have to subtract. And I won't make you subtract it 9 times on a test. Anyway, I'm not sure if you did or homework on it, I can't remember. But what does it do? Well, to be honest, what it did is it avoided you having to multiply anything or know your multiplication tables. Didn't it? All you had to know was the first number and a bunch of zeros. So some of you who have interest in special ed, this could be really helpful, right? Think about your students who have a real difficult time memorizing because there's a learning reason, not just because they're lazy. Okay, I'm not talking about those kids. Those kids just need to, start studying. But the ones who really have a reason for this being difficult, this becomes something that's more manageable. So there's a reason, okay? Now, let's take a look at the standard algorithm, which you all know and love, because it actually means that you have to know your multiplication tables in order to do it. So we're going to divide by 5, And you actually have to say to yourself, 5 times what equals 6, or as close as I can get. 1, right? How many times does 5 go into 6? It goes in 1 time. And you subtract. 6 minus 5 is 1. Again, I need to know my multiplication tables because I need to know how many times 5 goes into 12, which is twice. 2 times 5 is 10. Again, I need to know my multiplication tables to do that. And then I would subtract and get 2, and then I bring my 0 down, and I have 20, and 20 goes into 5, or 5 goes into 20 4 times. I don't get a remainder on this one. Again, it's the same problem I did before, but if you had, you would just write the or whatever after it. Right, you would do R2, exactly, just like on the last. So like on the last one, if you'd had a 2 at the bottom like that, you would have just had 124 R2 at the end. Okay, so we're working back in like 3rd grade, 4th grade kind of math where we don't have fractions that we're thinking about writing the answering just yet. All right. All right. Oh, goodness. 2, 3. All right, let me do one problem and then we'll let you go. I'll finish the next 2 next time. And we will start 3.5 next time. We won't finish because I'm just sure it's not going to happen. I'll let you guys decide if you want to do more of it in class with me talking or if you want more chance to do group work. I can do either way. Okay? All right, let's do one example. Juan, I don't know if that's say it, saved $53.40, $5,340 in 3 years. If he saved $95 per month the first year and a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? So we're doing a problem that's got some multiplication in there, maybe some addition in there. It's a word problem. You guys are familiar with word problems. We did chapter 1 together, right? All right, so what does this say we're going to do? Somebody tell me what you would like to do first. All right, so let's see how much he saved. That's what you mean, right? How much he saved the first year. I think it is, right? Not 2 years, but the first year. All right, so it says he saved $95 per month for the first year. So how do I figure out how much he saved for the first year? All right, so 12, because it's 12 what? Months. So I'm going to take 12 times 95. Okay? So you're going to take your 12 times 95, and somebody's going to tell me what the solution is to that, even if you grab your calculator. What is it? Close. 1140. So he saved 1140. This is the first year. All right, then what? All right, so 5,340 minus the 1140. Why am I doing this again? Good. So this is going to find out for me how much he made the last 2 years, or saved the last 2 years. What does this give me? 4,200. Then what? And then why am I going to divide by 24? Right, 12 months per year, 2 years. So 24 goes into 42 how many times? It's just once, yeah. Twice would be 48, so it wouldn't work. All right, what's 42 minus 24? 18. Okay, you're going to show the division. You're going to show the multiplication for this out too. I know we didn't, but pretend like we did for a moment. In whatever of the methods you choose. If you're not told a method, you can choose what you like. How many times will 24 go into 180? 7. What's 7 times 24? 168. Awesome. And I subtract and I get 12. 12? Yeah, and then I need to bring my 0. Sorry, I'm missing my 0 still. All right, and then 24 goes into 1200, or goes into 120 how many times? That is 5, and it actually goes in evenly on this one, right? Not all your problems will have no remainders, but they could. So now what? What's that? Do we have to? Okay, so make sure you answer the question asked. That's why I was asking that at that point, actually. Go back to the problem. It said, how much did he save per month during the last 2 years? And the answer is $175. Make sure you put your dollar sign on it, box in what your actual solution to whatever it is you found is, and then you're finished with it.